Hello and welcome back to the Science of Concrete Materials class. Today we will continue our discussion on the cement module. This is lecture number 6 of the class. This lecture's topic is the types of cement. So far we have covered, the following topics, the first 4 topics. What is cement, historical perspective, Portland cement manufacture, and the Portland cement composition. And today we will talk about the cement types. Okay, so as I said, today we will talk about the cement types, which are the Portland cements and other types. Okay, so first, not all cements are created equal, and cements are not all the same. You have to keep that in mind, as you will see. Knowledge of the compound composition of the Portland cement makes it possible to predict the properties of the cement. Also, manipulation of the compound composition can be used to modify certain properties of the cement so that the cement will perform more satisfactorily in particular conditions or certain applications. To understand and appreciate this, it is relevant to study, briefly at least at first, the hydration of each compound, each phase, and what it contributes to the overall properties. Of course, we will study the cement hydration process in more details in later lectures. So when Portland cement is mixed with water, its compounds undergo a series of chemical reactions, that are responsible for the eventual hardening of concrete. Reaction with water is the reactions with water are designated as hydration or called hydration, and new solids formed on hydration are collectively referred to as hydration products. So if we look at the first phase, the silicate phases, both phases, C3S or C2S, these react with water to form the calcium silicate hydrate gel and calcium hydroxide. The calcium silicate hydrate gel is what is responsible for the strength. The C3A, tricalcium aluminate, reaction, this reaction of this compound is slowed down with gypsum, as you see I'm showing here on this equation, because we add gypsum to the clinker to make Portland cement, so gypsum is present. So reaction of C3A is slowed down with the gypsum, to form a product called yttringite, which is the calcium trisulfoaluminate hydrate. If gypsum is not present, its hydration will cause flash set. Okay, so according to this equation, it will form yttringite, which is the primary yttringite I refer to. Okay, so in the absence, after this first hydration, first reaction right here, in the absence of enough supply of sulfate, yttringite converts to monosulfate phase as follows in this reaction. Yttringite will form with the remaining C3A plus water and will give us the monosulfoaluminate hydrate. Okay, at subsequent exposure to a sulfate source, yttringite reforms one more time according to this equation, which is the monosulfoaluminate plus the gypsum or the sulfate plus water will form yttringite one more time. This is really the essence of the sulfate attack. As I mentioned before, tringite formation is expansive. Tringite, formed during the early hydration, as I mentioned above, is referred to as primary ettringite, and its formation typically is accommodated while the concrete is wet or still in the plastic phase or plastic stage. Ettringite formed after concrete has hardened could cause expansion and cracking. But remember one thing for later lectures. This expansive property of ettringite, although harmful in this case, the formation of ettringite is the basis for the action of the expansive cement, which is a type of cement we will talk about in later lectures. Of course, other reactions. Just before that, as I mentioned before, in order to mitigate the formation of the secondary ettringite, the C3A content, or the ratio of the C3A to the sulfate content, is of importance in order to make sure we prevent the conversion to the monosulfoaluminate hydrate phase, so we prevent the formation of ettringite. This ratio here. Other reactions also could take place depending on the cement composition and the phases present. If you remember, I mentioned some of the minor impurities, such as the magnesium oxide, designated as MgO, and the free lime, calcium oxide. These products, when present, and since their hydration is slow and typically takes place after the concrete has hardened, these reactions are expansive and could cause damage. They could impact the soundness of concrete, as we will see later. The hydration reaction can be described, by the reaction stoichiometries, which is the rates of reaction and the heats of reaction. Also, in the case of cement chemistry, it is of interest to know whether the hydration products contribute to the strength of the hydrated cement or not. The hydration characteristics of the cement compounds are summarized in this table here. The stoichiometries are described by the chemical reactions, and they are outside the scope of this class, so I will not go to them in details. Okay, but as you can see, summarizes here, as I said, this table summarizes the compounds and their characteristics. For example, the C3S, which is tricalcium silicate, reaction rate is considered moderate. The amount of heat liberated is moderate also. Contribution to the strength, it's high, early strength, and the heat liberation is high. The C2S, the dicalcium silicate, reaction rate is slow, amount of heat liberated is low, the strength low initially and higher later, because it's slower reactions than C3S. It contributes less to the early strength and higher to the later strength. Heat liberation is low. The C3A tricalcium aluminate, of course, again, you always see this with gypsum, because that's the intent of adding gypsum to the cement. Its reaction rate is very fast. Amount of heat liberated is very high. Contribution to strength is low, and the heat liberated is very high. The C4AF tricalcium tetracalcium aluminoferrite, and again, it reacts with gypsum also to some extent. The reaction rate is moderate. The amount of heat liberated is moderate as well. Low contribution to the strength, and the heat liberation is moderate. Here, the rates of the hydration of these are pure cement compounds, are given in this figure right here. It can be seen that C3A and C3S are the most reactive compounds, as you can see here. the rate of reaction early on is very high. Whereas, C2S reacts much more slowly, as evident right here. One more thing to remember, which I have mentioned several times, the presence of gypsum slows the early rate of hydration of C3S. If you see this without gypsum, how the rate is much higher. With gypsum, it's slowed down. And that's really beneficial because it allows us to handle and transport and place the concrete eventually. Quantitative data are not available for the C4AF, the tetracalcium aluminoferrite, but the reaction of this compound, with plus gypsum and water, is believed to be somewhat slower than C3S, as I showed earlier. Whereas the hydration of C4AF without gypsum is faster. As I mentioned before, not much known about this phase. The rate of hydration of the compounds as they occur in cement, and I said that one here, these are the pure compounds, but these of the phases or the compounds as they occur in Portland cement, which refer to as impure phases. It's shown in this figure, where it can be seen that the A-light is the impure form of the C3S, and B-light, which is right here, which is the impure form of the C2S. They react more rapidly than they do as a pure pastes. If you compare it back to this slide, to this figure right here, the reaction is increased. The reaction rate is increased when impurities are present. As I said, the actual rate of hydration depends on the particular cements and its composition. It has to be noted, though, that both C3A and C4AF react with gypsum as well as water during hydration of cement. Okay, the rates of reactions need not really have a direct relation to strength development. However, as can be seen from this figure, clearly the calcium silicates provide most of the strength developed by Portland cement, as you can see here, C3S and C2S. All right. C3S provides most of the early strength, as you can see, in the first 3 to 4 weeks, right here. And C3S and C2S contribute equally to the ultimate strength, as you can see somewhere here. Oh, let me go back, sorry. The contribution of C3A and C4AF is very low, as you can see. And I mentioned this before also. Okay, so also, one thing to remember or to know, the hydration reactions of Portland cement are all exothermic. That is, they liberate heat. So during the hardening process, the concrete is being continually warmed by the internal heat generated due to this action. The extent of the temperature rise in a concrete section will depend on how quickly the heat is liberated and how quickly it is lost from the concrete to the surroundings. So therefore, the rate of the heat evolution is the important quantity. The contribution of each compound to the overall rate of heat evolution is a function of the heat of hydration, the rate of hydration, and the fraction of that compound in the cement. Yes, as you will see in a few slides. Why this is important, though, in case of mass concrete, we have large volume sections as compared to the surface area. Dissipation of heat is not fast enough which will result in what referred to as true adiabatic condition within the concrete. If the temperature rise, continue after the concrete has hardened, then stresses will develop and cracks will develop due to the thermal differential. So as shown in this graph here, the different types of cements, have different temperature rise. Of course, the type 3 cement, as I have probably mentioned before, is the highest rise, which is due to its higher fineness. I mean, it could be the same composition as the type 1, but much higher fineness, and that's what will cause it to liberate more heat or generate more heat. Types 2 and 4, vary in their composition as compared to type 1. Typically less C3S and or C3A contents. That's why the adiabatic temperature rise in a mass concrete section with these cements will be less than type 1. Here, this table is a more comprehensive table than the one I shown earlier. It summarizes the characteristics of each of the cement phases. Okay, and here in this table also I included the common crystal structures of the phases, which the impurities present in each phase, and more detailed information, because the fraction of each compound impact the characteristics of the cement, and also to a certain extent the common or the crystal structure. For example, the C3A between the cubic and orthorhombic, there is a difference in hydration rate and various other properties, just for general information. So as you can see here, we're showing here for each phase the approximate composition. For example, this is the 3-CEO SiO2, the C3S. This is the beta C2S. The C3A, which is the 3 CEOs and 1 Al2O3, and this is the tetracalcium aluminoferrite, the C4AF. This is the approximate composition of each. The abbreviated formula, as we have talked about this, you're familiar with this by now. This is the common mineral name. It's in the impure phase. So it is for the C3S, it's A light. For the C2S, it's B light. The principal impurities within C3S, you will find magnesium oxide, aluminum oxide, ferric oxide. Same with the C2S, when of course it's called B light at that time. Impurities within the C3A, you will find silicon dioxide, magnesium oxide, and also alkalis. And within the C4AF, the silicon dioxide or magnesium oxide impurities are found. The common crystalline form, monoclinic for the C3S, monoclinic for the C2S, cubic or orthorhombic for the C3A, although I've seen more cubic than orthorhombic, but I've seen the orthorhombic. For the C4AF is the orthorhombic crystal form. Again, here just some information I've shown before. This is the percentage of the compound present within the cement. The range from 35 to 65 for the C3S, 10 to 40 for the C2S. Again, depending on the type, you will see this later. C3A from 0 to 15, C4AF from 5 to 15. These are the average in the ordinary cement. 55, 28, and 8, we talked about them. The rate of reaction with water, and again, fast, slow, fast, moderate. Contribution to early strength, C3S good for the ultimate good as well. C2S poor for early strength, excellent for ultimate strength. C3A and C4AF are not really much of a concern when it comes to strength, but this is their contribution. The heat of hydration. Heat of hydration, medium for the C3S, low for the C2S, which is a good thing in certain types of cements. High for the C3A, medium for the C4AF. And this is the typical amount of heat, calories per gram of this material. You see the C3A is the highest, of course, followed by the C3S. C2S is very low, and that's why it's beneficial in certain cements. So now you have an idea on how, let me go back here. You have an idea on how to select a cement for a certain application. Like if early strength is important, for example, we need high C3A content. And of course, fineness in order to increase the rate of hydration and strength gain. If sulfate attack is an issue, as I mentioned, the problem with C3A. C3A and SO3 contents are important. If you are building a large section and heat buildup is an issue, you need to control C3S and C3A content. C2S, as I have been mentioning, is important, since if we reduce C3S content, we need something to make up for the low early strength gain, as higher strength gain later will be important. So C2S will be important, since, as I said, we need the strength gain. So now you have an idea of each compound and what it contributes and how it will impact the cement. You will see this. Okay, selecting really a cement is really performance-based, based on what is the function or the application you are intending to undertake. That's how you select your cement. The ASTM C150 has classified the Portland cement based on applications. This classification is referred to as OPC, which is ordinary Portland cement. According to ASTM C150, as I said, 5 types: 1, 2, 3, 4, and 5. The other classifications referred to as modified cement, those I will not discuss now. They will be discussed after we study the hydration process in details. So you will appreciate it more, because certain details are needed. But I will mention them here just quickly. We have other types other than the ordinary Portland cement, OPC. We have modified cements. Some of them are the blended cements, according to ASTM C595. We have ASTM C1157, which is performance-based cements. But in general, I said all cements are performance-based. We have the expansive cements, and I mentioned when I talked about Ettringite. We have miscellaneous type cements for various uses, like the masonry cement, rapid hardening cement, white cement, and oil well cement. We have also the non-Portland inorganic cement, so the calcium aluminate cements. These are not calcium silicate cements. So again, we will talk about all these in later lectures, not in this lecture, in detail, of course. As I said, the ASTM classifies the OPC into 5 different types, based on chemistry and intended application or function. The other types, as again, I'm repeating what I said, are performance-based cements. So we are in control of the cement by changing the chemistry during manufacture, for example, modifying the cements by blending with other materials like the SCMs in case of the blended cements, or both of the above. So we can do both to come up with a certain cement that suits a certain application. So let's look at in a bit of a detail about the ASTM C150 types. There are 5 types: 1, 2, 3, 4, 5. Let's go to in more detail. We have type 1. This is the general use everyday cement. Okay. We have type 2. This is moderate heat of hydration and moderate sulfate resistance cement. When we have any of these situations, we need moderate heat generation and moderate sulfate resistance. When the situation is not severe, we could use this. So this cement, it is characterized by having a C3A content less than 8%. This is used for general construction, seawater construction, and mass concrete. Again, this is general use, but we need less heat generated and moderate resistance to sulfate. So as again, there is a limit on C3A sometimes. Cement, are classified by the producers as type 1/2. You will see them because the limit is on the C3A. So some cement, because the requirements of ASTM are, vary widely, and it does not impose restrictions on everything. So the cement could actually meet the designations of type 1 and 2 at the same time. Okay, we have type 3, which is designated as high early strength. C3A content is less than 15%. This one is used really in emergency repairs, in precast concrete, in winter construction. Because, we need it where we need strength very fast. As I said, in emergency repairs and winter construction. This though can be type 1, but with ground to higher fineness. If you remember, I talked about the fineness. Grinding to a higher fineness costs money. It's very expensive. So this cement type also expensive as a result. So using this should be really considered with care. Type 4, this one designated as low heat of hydration. Type 2 is moderate, this one low heat of hydration. It has these restrictions: C3S is less than 35%, C3A less than 7%, because that's really what generates the heat. C2S more than 40%, because we need more C2S to make up for the low C3S content, as the strength gain dependent on the calcium silicate contents. This one is mostly used in mass concrete, where we need to reduce the heat generated. Okay, this I have to say though, this cement is rarely produced anymore, since low heat generation can be produced or can be achieved by different ways, such as using supplementary cementitious materials such as slag or fly ash, where we can reduce the heat generated. So this one, you may not find this cement available, the type 4. The type 5 is the sulfate resistance cement, where we have, severe sulfate problems, in the soil or for sewer structures. There is a limit on C3A, less than 5%. As I mentioned earlier, C3A reacts with sulfates and creates the compound that could be, in certain circumstances, detrimental to concrete. So this table really summarizes the cement types we mentioned so far. The other types I mentioned before in the previous slide, again, will be studied after we study the cement tests and hydration process, so the student can really can have more appreciation for the properties and other aspects. Okay. So just let's mention a few more things here. The typical compositions of ordinary Portland cements are shown here in the next slide. I will show it. The ASTM C150 imposes limits on chemical composition, and it have some optional limits as well, as you will see. The heat of hydration varies, as I will show on a graph on the next slides. The ultimate strength gain does not vary much, since the total of C2S and C3S is almost identical in all 5 types, as you will see. Okay. The ASTM C150 has a designation for each type with the letter A, like 1A, 2A, 3A, 4A, and 5A. This means, air entrained cements. Okay. But these air entrained cements with the designation A are not really common, since it is basically preferred by most concrete producers to use air entraining agent when there is air entrainment requirement. Okay, so those are not common. I am not really I don't really use them. I have never used them, designation A cements. Okay, also much of the required properties, remember about the performance-based, much of the required properties can be obtained by blending cements with certain additives. As I mentioned, the supplementary cementitious materials such as fly ash, slag, and the metakaolin, etc., to get the required performance. Okay, so we have, a performance-based cements designation by ASTM, which is ASTM 1157. It has, 5 types, and these 5 types actually parallel the 5 types of the C150. As you can see, we have the GU, general use cement. This is hydraulic cement for general construction. We use it when one or more of the special types are not required. The special types here shown below. The HE, which is the high early strength. The MS, moderate sulfate resistance. The HS, high sulfate resistance. MH, moderate heat of hydration. And low LH is the low heat of hydration. Okay, so these cements, as I said, performance-based. And again, you could designate them or you could specify them. Basically, what you're doing, you are speccing out certain performance, not a cement. Okay, so but one has to be really familiar with what goes on in the hydration process and what comes out. So basically, you designate certain performance, and the cement and the concrete producer has to comply with such requirement. Also, we have, as I said, the ASTM C595, which is the blended cements, and the other types I mentioned earlier. Okay, so let's look here, as I mentioned, as a typical chemical composition and properties of Portland cements. The ASTM types 1 through 5. Type 1, 2, 3, 4, 5 here. The C3S, as you can see, type 1, 55, type 2 is the same, did not change. Type 3 is the same, but look at the fineness, 550 versus 365. That's really what makes it type 3. Okay, the C2S, it's 18%, 19, 17. Look at types 4 and 5, where we have lower C3S, for example, 32%, type 4. The C3A, of course, look at type 2, it's less than type 1. This is the moderate sulfate resistance, moderate heat of hydration. The type 4 it's less, the type 5 less as well. C4AF, not much of a concern. The gypsum here is almost the same, but of course we have less here because of the less C3A content. The fineness, as you see, this is the typical value for a type A. Type 2, close. Type 3 is much higher. Type 4 and 5, type 4 is less. Type 5 is the same order. Compressive strength, this is 1 day in MPa, of course, and as you can see, 15 MPa, type 2 close, type 3 24, type 4 is 4, type 5 is 12, so less early strength. The heat of hydration, as we expect, 7 days, joule per gram. Look at this compared to this, compared, for example, to this, the low heat of hydration cement. Okay. This one here, it gives us, I talked about somewhat about this, the adiabatic condition, you know, the heat evolution measured as, you know, rise in temperature of mass concrete. Look at the type 3 is the highest. This type 3 is type 1, but ground much higher. Look at type 2 and type 4. If you look at the slide before, it makes sense. Okay. And again, if we have a problem with, in case of mass concrete, of course, you do not yet use type 1, you do not use type 2. You use type 3 rather. You use type 2, and if it's even more stringent, you could use type 4, but I said this is not produced almost anymore, so you will have to resort to blended cement or blending cement with some of the SCMs. This is the rate of strength gain. Again, as you can see, type 3 is the highest early strength. Type 1 is the middle between all type 5. Type 2 and 4 less. Type 5, type 2 and 5. Type 4 is the lowest, which is, this is the low heat of hydration. It has the lowest C3S content. So basically, but ultimately, you know, we said this is high early strength, but if you look at it, later strength is less. And for these three other types, 4, 2, and 5, they have higher later strength because they have higher C2S content, which is responsible for the later strength gain. Okay, as I mentioned, really, the remaining types, which I'm going to list in the table below, will be discussed, you know, after studying the cement hydration products, in addition to studying the mineral admixtures, in order to have full appreciation of the actions of these cements. Okay, which the types, as I mentioned earlier. As I mentioned again, though, generally speaking, all cement types are performance-based, and the engineer is responsible for specifying the cement based on the application's requirement. The engineer must be completely familiar with the cement composition and the cement specifications, you know, ASTM requirements and other requirements, in order to be able to review and vet the proposed materials from the concrete supplier, for example. This is a must, in my opinion. So if you are not familiar with these requirements, you can review the ASTM designations or any other source in order to be familiar with the requirements imposed by ASTM or by codes sometimes, the building codes, which of course reference ASTM, or you consult your particular job specifications that you have to comply with 100%. Okay, these are the other types. I just summarized them here so that you have them for reference for those later lectures I talked about. We have, you know, the blended cement, various types. We have the expansive cement, for example, type E1K. We have these special cements, the 4 types. We have the non-Portland inorganic cements, the calcium aluminate and the gypsum plaster. This is for reference. I will talk about those in later lectures. Here though, in the next 4 slides, I'm going to show some tables I extracted from the ASTM book, and they show some of the standard and optional chemical requirements and limits of the ordinary Portland cement, the 5 types. Some other properties, are mentioned, such as the physical requirements, which will be covered in more details in the next lecture or 2 when I talk about the tests on the cement, the physical properties, fineness, and other properties. But here, for example, this table 1 shows the standard composition requirements for the various types. What are the standard requirements? If it's blank here, there is no standard requirement, okay? This table here shows optional composition requirements, optional. Let me go back here, and again, this is the cement types here, and here the applicable tests method to determine these properties. We talked about ASTM C150 about the chemical composition, the oxide chemical composition. Okay, so basically, again, you have to be familiar. You could read it, and if you have any questions, you could ask. This one here shows optional requirements. For certain the cements, what are optional, not standard requirements. Okay. This one, although not very clear, this is table 3 from ASTM C150. It shows the standard physical requirements. What I mean by physical requirements, if you look at it here, the air content of the mortar made from this cement, of course, there are certain requirements. The fineness, the air permeability, based on air permeability test, the STM designation shown here. The autoclave expansion, strength, compressive strength. These are physical, as I said, physical requirements, standard physical requirements that are required by the concrete producers to provide this information when they submit that cement mill certificate. Of course, we have the set-in time. Again, we have the by both tests here based on Gilmore test or VICAT test, depending which test is being reported. Okay, so this is a good reference really to look at it, become familiar. What are the standard physical requirements that should be provided by the cement producer or the concrete producer who is supplying the concrete to your job? This is table number 4. These are optional physical requirements, not standard. Like, false set, final penetration, heat of hydration. Although the heat of hydration, almost on every mill certificate, I see it. The strength, compressive strength, and the sulfate resistance. Of course, the sulfate resistance, if we are using which type cements, it become a standard requirement. Okay, and again, I would advise that you go through these 4 tables, become familiar with them, and just as I said, to know what are required, what are the standard and optional requirements that needs to be provided on the cement mill certificate. Okay, this is it for this lecture. I know I have gone longer than I planned probably for its duration, but anyway, thank you. Thank you for listening. The next lecture, we will probably talk about the cement tests, the tests performed in Portland cement. So thank you for watching, and I will see you next lecture. Thanks again.